Okay, good afternoon to everybody. My name is Javier Nogueras, and I am Professor of Computer Science in the Computer Science and Systems Engineering Department. Okay, so if you go to Moodle, we are in this session, Fundamentals of Object Orientation. And here you can find the slides that I will present now. So more or less, I will dedicate 1 hour to present some theoretical concepts, and later we will try to do some exercises that you have here. The slides is this PDF document, and for the exercise you have here a Markdown document. No, sorry, I click on a different one, but you can see it here. Okay, you can see the exercises that we will make in the second hour. Okay, so now I will stop sharing the browser, and I will present directly the slides. Okay. If you have any doubt, you can interrupt me at any moment. Okay. Okay, so the idea is to present some fundamentals of object orientation. I don't know if you are very familiar with Python. Probably you have done some programming with Python, but maybe you don't use usually the concepts of object orientation. So I will try to present quickly an introduction to object orientation, and I will try to present the main concepts of object orientation and how we can translate these concepts into the Python programming language. Okay. After that, in the second hour, we will dedicate some time to make some exercises. And at the end of these slides, you can also have a look at some bibliographic references. Okay, so what is the origin of this object orientation? Well, in principle, the idea is that in general, we want to build software with a good quality. And we try to apply something that we call software engineering. It's a discipline, or let's say a coordinated application of techniques, methodologies, and tools to produce high quality software within a given budget and by a given date. So the idea is that, in contrast to the first times of software production, that in those initial times, the production or the programming was quite an artisanal task, okay, made by experts. The idea is that once a client has some customer needs, we can apply some methodologies, techniques, and methods in a systematic way to produce software with a given budget and by a given date. Okay. When we mention high quality software, the idea is that the software that we produce has some attributes like the ones that we present here. So we aim to have a software with a high functionality. What is functionality? The degree of certainty that the system processes the information accurately and completely. We also want to produce a software that is flexible. What does it mean? It means that the user may introduce some modifications in the configuration of the software in order to customize the system without changing any line of code. On the other hand, we want also to maintain the software in an easy way. I mean, Usually, once you develop a software, you deploy it, new demands arise from the users. Or maybe we need to adapt the system to a new operating system or to a new environment. So we want to have a software that can be easily adapted to these modifications, or that can be easily corrected if we detect some bugs, some errors in the code. And on the other hand, for instance, we want also to have a software that is reusable. I mean, we try to build the software in such a way that some components can be reused in other projects. So this way, we made the software more scalable, and we don't spend so much time in projects that are similar. There are other attributes. For example, efficiency, user-friendliness, portability. All these attributes configure or set up the quality of the software. A good mechanism to face these objectives of flexibility, maintainability, and reusability is to try to make the software modular. What does it mean? That when we have a complex problem, we try to divide the problem in small problems that can be probably solved in an easy way. So we try to make small pieces that build up the complex system that we want to produce at the end. Okay, so modularity is a good mechanism to try to produce software with high quality. Okay, we apply something that is well known. We try to divide and conquer. And let's say that object orientation is built around this idea of modularity. Okay, when we talk about methodologies for software development, a methodology, to explain first, is a collection of methods, notations, processes, and tools applied throughout the development process. I mean, through the analysis, the design, the implementation, and testing. And the way methodologies are classified is usually through the way that they structure the software. On the one hand, we talk about structured methodologies when we talk about methodologies that try to divide the software in functionalities. These were the first methodologies that arose in the industry of software. We try to divide a system into subsystems, and then in functions, and then in processes. And another methodology that is newer than the structured methodologies are the object-oriented methodologies. In this type of methodologies, the way that we organize the software is considering that everything are objects. The system is a collection of objects that are interacting all the time. An object can be everything: a concept, an abstraction, a physical entity, almost everything. For instance, in our software, for example, a person like Donald Trump, or a company like Google, or a table can be modeled as objects. And we say that a system or a software that is based on object orientation models or mimics or imitates very well the real world, because everything are objects, and we establish also relationships between objects. Okay. Okay. So the main idea in this slide and the previous slide is that objects are very well matched to this idea of modularity. The objects are small modules that encapsulate state and behavior, and the status represent the current values of the properties, the attributes, and the relationships, the bindings that we establish with other objects. When we execute a system, a software, with as the time goes by, the object is evolving and the status is modifying because the attributes are going to have a new value. Okay. On the other hand, when we call behavior, we are referring to the set of operations of the object. They are the actions and the reactions that an object may have. Okay. Okay. The idea also of object orientation is that when we develop the software, when we start with the analysis, and when we move to the design and the implementation, we have a very gradual transition. Okay, so we move and we try to use the same concepts in both analysis, design, and implementation. Okay, and usually for analysis and design, I don't know if you are familiar, but we use a notation, a graphical notation that is called UML, which stands for Unified Modeling Language. It's a graphical notation where we can make an outline of the code that later we will implement. But let's say that we are going to build some diagrams that we can discuss between developers or researchers before having the final implementation. There are many types of diagrams with this notation. Some diagrams are focused on describing how the software is organized. And we talk about class diagrams, package diagrams, deployment diagrams. In these 2 hours, we will focus mainly on class diagrams. On the other hand, we can also describe the behavior that our software will have. And for this, usually we employ use case diagrams or sequence diagrams. Okay, so they help us to describe how our system is going to behave. Okay, when we execute a software and application. And well, apart from these diagrams for analysis and design, later we are going to implement. But the concepts and ideas that we have in our programming language are very similar to the concepts that we employ in analysis and design. Okay, so in many of the following slides, I will present a small diagram to describe more or less the example that I want to show. And later you will see that in the code, the concepts that we use in the Python code, okay, reflect directly what we have in the diagram. Okay. So now I will present some key concepts that are very characteristic of the object model. Okay, so we say that in object orientation, the main features are that we want to provide a mechanism for abstraction. We want to focus on the essentials of the objects. On the other hand, with object orientation, we try also to provide some encapsulation of the low-level details of the implementation. In object orientation, we will also provide mechanisms to establish hierarchies of objects. We try to order or to distinguish different classes of objects. Okay. Another characteristic that is interesting in object orientation is the possibility to send a message to different objects, the same message to different objects, and every object reacts in different ways, maybe related because it's the same message with the same grammar, let's say, but maybe the semantic of the execution of this message is different in every object. This is called polymorphism, and it's very interesting because this allows us to make the software quite general, okay? And again, we recall the idea of modularity. All the concepts in object orientation are or aim to provide mechanisms to devise the code in coherent and cohesive small pieces, okay, that work together for the final software. Okay, so now after this introduction that we try to motivate why object orientation is interesting and the role of object orientation in software engineering, we are going to present these 5 concepts in the context of Python, okay? So the idea is that we will see how to reduce the complexity of programs and try to have a code that models more in a more realistic way the world or the part of the world that we want to reproduce in our software. Okay. Okay. I'm going to show in the slides some examples, and if you want to have directly the code of these examples, you can have a look at this public repository where I have uploaded these examples. Okay. I am presenting now directly the PDF of the presentation, and it's not easy to move to the repository, but maybe later, okay, I can show you how this works if you want to run directly the examples with Visual Studio or maybe another tool that you are using for programming in Python, okay? So first, we present in more detail the idea of abstraction, and later we see how to translate this concept in Python, okay? So the first idea is that we want to define some abstractions in the problem that we want to model inside the software, okay? As I said before, almost everything can be an object, a person, a company, or a table. If we want to model this when we try to analyze the software that we are going to build, and we want to model this in a class diagram using the UML notation, we are going to use this kind of box where we have 3 compartments. A compartment for the name of the class, a compartment for the attributes, and a compartment for the operations. The attributes are used to model the status of the object, and the operations are to model the behavior of the objects, okay? And a class means that there are several objects that behave and have a similar status, so it's a way of grouping objects, okay? If we move this idea to our Python code, we will see that, for example, here I have the dog class, okay? I don't provide any details for attributes or operations, and if I want to translate this concept into Python, in the scripts, in the Python scripts, I have the possibility of using the reserved word class, okay? And later I give the name of the class. in this case dog. Okay, I don't have anything else. Okay, but if I run this script in my environment, for example, Visual Studio, okay, if I open the Python console, okay, I can define a variable and I can instantiate with an object of the class dog. Okay, I can instantiate another variable called b, and I can compare a with b. Okay, in principle, this comparison returns a false value because what I am comparing now is the internal identifier of the objects, and I have created two different objects, so it's logical that the result is false. Okay, is false. Okay. You have any question, just interrupt me. You can interrupt me and I try to explain better. Okay. Okay. In any abstraction, I can also incorporate some attributes, okay, that are properties of the different objects. Okay. If I try to incorporate attributes in a class diagram, what I will do is to use the second compartment. For example, I can have a person class with three attributes: a name, the age of this person, and the weight of this person. Also, if I need it, in analysis or maybe in design, I can annotate here. This is only just for a common understanding between designers, between developers, before implementing, okay? Because when you build a complex code, it's good to have a map in the same way or to have a plan in the same way as architects probably work for a long time before starting to build a house or a building. So for programmers, for developers, this is also logical. Okay, we can draw in a piece of paper or using a case tool, a tool for computer-aided software engineering. I can make a small diagram before deciding that this is the right approach for implementation. Okay, so here I provide some properties. I establish also the types that are more appropriate. Okay, and this is what I should use in analysis and design. Okay, let me see. Okay, and the same. I will do the same for the operations, for the behavior of the objects that belong to a class. Okay, I can use the third compartment to provide some operations that can be applied to the objects of a class or that can be invoked by the objects directly of this class or from a class in the same software. Okay, so for example, for a person, now I have defined a third compartment and I have incorporated an operation called change address. And probably this operation modifies the value of the attribute address. Or here, for example, I have a geometric object with color, with a position. It can be a circle, a square, whatever. Okay, and I have added two operations. Maybe I can move using some degrees this geometric object. Okay, if I am designing an application to draw geometries, or I can select a point in this geometric object and I add a select operation. Usually the operations that in implementation are called methods may have arguments. For example, in the case of move, I can establish a parameter where I will send the specific number of degrees of this movement. Or in the case of select, I can indicate the point that must be selected within this geometric object, okay? And in some cases, the operations may also return a value. So here in UML, I indicate that this is a Boolean value, okay? There is also something that is typical in every programming language, and is the possibility of defining constructor methods. Methods that are used to initialize the values on the object that I have just created, okay? And if I translate all the concepts that I have just mentioned in the previous slides to Python, you will see, for example, that here my objective is to define a class called dog. I have two attributes for this class, name and age. And in the diagram, I have also incorporated an attribute that is called species, okay? And you can see that I have underlined species equals canis familiaris. In the UML notation, whenever you see an attribute or a method, an operation underline, this means that this is a class member. What does it mean, a class member? It's an attribute that contains the same value for all the objects in the class, all the objects in the class, or a method that can be executed without having a specific instance of an object, okay? Okay, so how I translate all these concepts? Okay, so my dog class, okay, now apart from using the word class before the identifier of the class, okay, I have also added a class attribute, species, okay? And species equals canis familiaris. So this means that every object that I instantiate from this class is going to have the same value for a species. Another thing that I have done is to define a specific constructor method. In Python, the constructor methods are using this special identifier, which is called init, and using as preface a double underscore, and as a suffix a double underscore. The instance attributes, the attributes that are particular for every object that I instantiate, are created within the scope of the body of this method called init, right? So for example, here, the instance attribute means that it's not a class attribute, okay? So it's particular for every object. So here you can see that the name, I have defined an attribute name and an attribute age, okay? Another special word is self. Self is a reference to the object that has been just instantiated, okay? And this is the way to refer to the instance attributes or to the instance methods that I define in a class, okay? If you have any doubt, you can stop me, okay? No problem for that. Okay, so in the box highlighted in blue, I have the definition of the class in Python. In the box highlighted in orange, I am showing the result of writing some code that is directly interpreted by Python. Okay, so on the right side, you can see that I have created a variable identified as miles. Okay, and I have created the doc instance using the name of the class, and I use as parameters miles, the string miles, and a second value that is 4. Miles for the name, 4 for the age. Okay, you can notice that I'm not passing anything for self. Self is something that is created implicitly when I invoke the constructor. Okay, when I use dot here, it means that I'm going to execute this method, and directly the Python interpreter is going to create this reference to the object that I can use inside the body of init or any other instance method that will receive this special parameter. I could have used another identifier instead of self, okay? But by convention, I always use self, right? I don't know if you have programmed in Java, but in Java, for example, they have decided that this internal reference is the word this. Okay, so self would be something similar to this, if you are familiar with Java. Okay, okay, I continue with the example. Okay, so when I can create another variable with identifier body, and if I access the attribute miles.name, you can see that for accessing the attributes, I use the dot notation miles.name. Okay, I will generate or I will return the value miles. If I use the same notation with body, okay, the value will be body. But this is just to remark that every object has its own values for name and age, okay, because these are instance attributes. In contrast, if I invoke body.species, this is going to show canis familiaris. If I modify directly a species, I can modify a class attribute just making reference to the name of the class dot and the name making reference to the name of the class dot and the name of the class attribute, and I assign perro. Okay, when I invoke body.species, the result will be perro because I have modified the value for every object in the class. Is that okay? Perfect.
I have one question from this slide that you said at the beginning. The the little square on the right of the presentation that says like dog and then species and it's underlined. And you said it was important that it was underlined. I didn't really quite understand because the other things I see on the screen are code, but that square you talked about it as if it was important that it was underlined. I didn't
Yes,
quite
yes.
understand.
This is UML. This is a
Okay.
class diagram that we use before going directly to the development environment. So when you are several people in a team, probably you have some meetings where you discuss how you are going to implement this problem, okay? How you are going to face the development of the software. So we have some conventions when we provide these analysis diagrams or these development diagrams. And one of these conventions, one of the notations that I use in UML diagrams is that for proposing the definition of a class, I use this box. This box has 3 compartments. The first for the name of the class, the second compartment for the attributes. And in the case that some of these attributes are going to be class attributes. I mean, they are going to have the same value for all the objects. I underline them. So this is just a graphical notation to understand that, for example, you can be the analyst in this project, in this software project, but maybe you subcontract another company for the implementation. So the information that you provide to this third company for implementation is the class diagram. And they are going to understand that they are going to define this species as a class attribute.
Okay. You call it a UML diagram.
Yes, this is a
Okay.
UML diagram.
I had never seen, I didn't know about it. Okay, thank you.
Okay. I tell that because this is interesting that you learn that usually before implementing, because I know that even students that are studying computer science, they like to program directly all the time. It's important to think before the implementation. And okay, I told you that object orientation tries to be quite transparent between analysis, design, and implementation. So we make a direct translation of the concepts that we have in analysis and design into implementation. Okay, so this is what I wanted to reinforce. Great. More things. Apart from the constructor, we can also have some methods that are particular for an object. Okay, so now, for example, in the class doc, we are going to define an operation that is called description and an operation speak. Okay. In the case of description, you can see on the left, on the bottom left corner, that we have defined an instance method. The instance method is another method that, using the indentation that we usually employ in Python for everything. Okay, so this is within the scope of the doc class. Okay, and you can see that this is also an instance method because we have here also this special parameter called self. Okay, the idea of this operation, okay, the semantics behind this operation is that we are going to return a string providing a description of the object. For instance, we are going to return a formatted string. This is why we use f, and we use then the double quotes, and inside this kind of brackets, these key brackets, we are going to incorporate in the string the name of the object and the age of the object. Okay, and we can also define a second method, a second instance method, that apart from self, it also receives an additional parameter, an additional argument, which is something representative for the sound that the doc is going to emit. Okay. Here, well, it's something very simple. So we just return again another string with the name of the dog, and we just say says and something more or less imitating the sound. Okay. And on the right side, we can see how we have defined an object called miles. We have instantiated the object with the dog identifier. We have passed miles and 4. If we access the method, we use again the notation with the dot. Okay, so every time that we invoke an instance attribute or an instance method, we need to put to type the identifier of the object, dot, and the name of the method or the attribute. Okay, so if we access miles.description, okay, we are going to return this string. Miles is 4 years old. If we invoke speak and we pass the value poof poof, we are going to return Miles says poof poof. Okay. If you want, I can try to execute this smallest sample. This is called doc3.py in Visual Studio. I don't know if it is interesting or not, but you can see how this works. I am just changing. One moment. And this way I make sure that I don't have problems to share the screen of Visual Studio. Okay, so for example, I think that you can visualize this small sample. Okay, so I don't know if you are doing that by yourselves, but you can clone the repository. And here you will find in the code folder all the smallest samples. Every time that in the slides you see doc1.py, doc3.py, then this refers to this small script. Okay, so anyway, you can see that when if you click just for the direct option run Python file, this is going to work perfectly. Okay, so in this case, for example, you can see that I am invoking the main function. Okay, and I am creating this variable called body, and I try to print in the standard output body.description, body speak, Miles description, and it works perfectly. Okay. I don't know if this is interesting or not, but if you don't want to use Visual Studio, but maybe you want to use directly the browser, one thing that you can do is to use the Google Colapse. Okay. I don't know if you are familiar with that. I will just dedicate 1 or 2 minutes to this, but you can go to your Drive folder if you have an account in Google, and you can create here a Google Collaboratory. So this will create an space where you can paste some code, for example, here. Okay, so you can copy this code, for example, and you can copy that here, and you can run this cell. Okay, and this is also a possibility. And later you can add a new code cell and you can try other possibilities. Miles equals doc miles. Okay, and then you can run and you can print miles dot description, something like this. Okay, and this is also something very easy that you can use to try some of the concepts that we have just presented. Okay, good. Well, I will move back to the presentation. Okay, good. So let's advance a little bit. Okay, another relevant concept in object orientation is the possibility to provide encapsulation. So starting from analysis and design, we focus or we try to provide mechanisms to define ways to hide low-level details in our code. Okay, so what we saw before is that abstraction is focused on the external view, on the external properties of objects. With encapsulation, we provide some tools and mechanisms to encapsulate or to hide some low-level details. Okay. The notation UML and in general in object orientation, we say that the members of a class can have 3 levels of visibility. Okay, on the one hand, we can say that a member is private, and we define a member as private when we think that this is only relevant for the implementation of a class. That is to say, a private attribute can be only accessed by the body of the methods defined inside the class. A private operation can only be invoked by the class where it is defined within the body of the methods inside this class. And the private attributes and operations cannot be accessed by other classes independently if they are subclasses. Okay, we can also define another level of visibility that is not so restrictive, that we call that protected level. We define a member as protected if we think that we are going to need this member. It doesn't matter if it is an attribute or an operation in a subclass. Okay, later we will see how the hierarchy of inheritance works. But the idea is that when we don't want to be so restrictive, because probably in the implementation of a subclass, a class that derives from another class, needs something from the superclass, from the parent, then we are going to declare this member as protected. Okay, and finally, there is a public level of visibility. We define a member as public when we think that this member is necessary by other classes in my software. Okay, it can be accessed by any class. Okay, how does encapsulation work in Python? Well, the reality is that this programming language doesn't have something very special to distinguish between a private, a public, or a protected member. Okay, so the only possibility to define something as private is to use a convention for the naming. Okay, I forgot to say that in UML, when we try to define graphically that something is private, we are going to use a minus sign. When we consider that something is public, we are going to use a plus sign. Okay, and for protective, we are going to use this symbol. I don't know how to call that in English, but okay, you can see that. Okay, this has a special symbol that is also used for musicians, by musicians. Okay, so this is the graphical representation in UML, but as I tell you, in Python, we don't have any real way to translate that very directly. Okay, so what we are using in Python is just a convention. This means that nothing prevents us from accessing this member, this attribute, or this method, but we can see that whenever someone has defined something with an initial underscore, this means that the person that defined that class thought that this member should be private, shouldn't be used by other classes in the software that we are developing. Okay, so here you can see that we want to define name and age as private attributes. And inside the init method, we have used dot underscore name. Okay. So here, what we have also added are two additional methods to update the value of an attribute and to return the value of an attribute. Okay, so for example, age should be also a private attribute, for instance. Okay, so what we do here is that instead of modifying directly the value of the attribute, we should use setAge or getAge to get access to the value of this attribute. Okay, on the right side, you can see that I have declared an object of type doc. I can access the private attribute because this is just a convention in Python. It's not recommended, but I can use that. But the recommended way is that I always use the instance methods setAge and getAge for this. Okay. I hope that is clear. Another thing that I can use to protect better the access to something that I consider as private is a mechanism that is called name mangling. Name mangling is when I use a double underscore for an attribute or an operation. For example, here I have defined the attribute for the name and the attribute for the age with a double underscore, a double initial underscore. On the right side, you can see how this works. If I try to access now with the notation miles dot underscore underscore age, I will generate an error in my Python interpreter, right? Why? Because when I use double underscore, if I want to access from an external code, the name of the attribute is transformed into underscore, the name of the class, double name of the class, double underscore, and the name of the member. Okay, so if I type miles dot underscore doc with capital D and then underscore underscore age, then I have access to the age of the dog. Okay, so let's say that with this name mangling, I am complicating the access. I am trying to prevent users of this class to access directly this member. Is it okay? Okay. Let's go now to explain additional concepts. Okay. So let's start with the possibilities to define hierarchies. Okay. We say that when we start learning, we have like 3 different ways of organizing our thinking. We can identify entities through its attributes. We can distinguish between different classes of objects. We can distinguish models from journalists, actors, students, teachers, and we can distinguish between objects and the parts of an object. We can distinguish that a car consists of wheels, seats, doors, these kind of things, okay? So in object orientation, there are two additional mechanisms to establish these hierarchies. On the one hand, we can define an inheritance hierarchy. We can distinguish between something that is more general and something that is more special. And we can also establish relationships between objects because there are associations between objects, or one object aggregates other objects, or because one object consists of other objects. Okay, so we can have generalization, specialization relationships, and we can have structural relationships. Okay. The inheritance hierarchy is also known as is-a relationship. So, for example, we can define that class animal is a superclass of the person class, or that animal is the parent class of a person class. Okay. The inheritance hierarchy also allows us to inherit members in the parent class. So for example, here we have defined the class animal with an attribute called age and an operation that is called sleep. Persons are also animals, but they have additional attributes. In this small example, they can have also an additional passport number attribute, and they have an additional operation that is called study. Okay. How we can translate this idea into Python? Okay. For example, here I can define a special class to identify a particular species of dog. Okay, so I can have bulldog, border collie, and I have the general class of dogs. Okay, so for example, here in my small box with the Python code, I have defined the class border collie. To identify the parent class, I have enclosed within parentheses the name of the superclass, the name of the parent class, that in this case is dog. Okay, and I have also defined another subclass that is called bulldog that also inherits from dog. Okay, if I create now objects, I can invoke to the constructor border collie. It will inherit the constructor of the parent class. Okay, and okay, I can reuse some of the methods that were defined in the superclass. For example, you can have a look here, okay, on the left side, and you can see that I have defined a special method called underscore underscore str underscore underscore. Okay, this is a special method that is recognized in Python. That means that with this method, I'm going to return a string representation of the object. Okay, this method uh, is inherited by the subclass border collie. So when I call here print and I put inside parentheses Robert, the Python interpreter understands that I want to provide a string representation. The string representation provided by the special method underscore underscore str underscore underscore. is not defined in border collie, but is defined in the parent class. Okay, so I will show, this will show in the screen, Robert is 8 years old. If I invoke to this function, I'm going to retrieve, this is a special function in Python that returns the class of this object, and it returns border collie. And there is also a special function that is called isInstance that is going to telling me whether Robert is an instance of border collie. The result is a Boolean value, and in this case is true. Okay. More ideas. Okay. In the subclasses, of course, I can redefine members. I can redefine methods, okay? And I can reuse the behavior in the parent class, okay? So for example, here, I have redefined the method description and the method speak for the class border collie, and I have added an additional attribute that is called play frisbee. I can see the implementation of border collie, and here I have defined a constructor with 3 parameters apart from self. I receive a value for the name, a value for the age, and a value for the new attribute that is called play frisbee to indicate if this dog is able or likes to play frisbee, okay? Which is something typical for border collies. I don't know if you have a border collie, but this is something very typical in this species. Okay, it doesn't matter. This is just an example. Okay, so I am going to reuse the behavior of the constructor in the parent class. How can I do it? I can use the word supper, parentheses, parentheses, and I can invoke the constructor in the parent class. And then I add the part that is particular for border collies. The same for the methods. Okay, for example, here the description method, for example, can be implemented in such a way that if the value of play frisbee is true, then I return. In this case, I am just redefining completely the implementation of the description method. Okay, and I just say that if it plays frisbee, I'm going to return this message. If not, I'm going to return this another message. And in the case of speak, I am reusing the behavior of the parent. Okay, the only thing is that now I am adding a default value for the parameter shown, and I'm going to reuse the method in the parent, okay, and I invoke that, okay. You can see that it works, okay. I can create an instance of border collie, I can invoke a speak, and as I have this default value that it wasn't available for the parent class, I can return this string. Robert says whoa. Okay. Okay. Let's move now to associations. Okay. So we can define structural relationships between objects. Okay. For example, we can establish in our analysis model, or while we are thinking about how to implement a code for a project or the software that you want to develop for an experiment, depends on the context where you are using your programming. Okay, I can establish, for example, that I'm going to create a person class and a company class, and there is some kind of relationship. For example, a person works for a company, or an airport is located in a city. In UML, if I want to denote that in a class diagram, I am going to use a line connecting the both classes. Okay, so I can give a name for the association. Apart from that, I can also add something that is called role. Okay, it's a noun usually that allows me to understand the role played by the object in one stream of the association. So, for example, a person, we can have an object of the type person that works for a company that is, for example, Google. So one person works for Google. Google plays the role of being the employer of this person. And this person plays the role of being an employee for that company. Okay, so I can identify roles in association, in the different associations that I define. I can also put an additional detail in the association, that is the multiplicity, the number of objects that I consider as a minimum or as a maximum that are linked with another object. Okay, for example, and the notation is that I use a number for the minimum, then I have two dots, and then I have a number for the maximum. So here, for example, that is more easy to understand. A company may hire between one and many employees. When this many is not defined, we use this special symbol that is the asterisk. Okay, this star. Okay, the same for the person objects. A person in his professional life can work for many companies. When this is not really defined, we don't have a specific number as maximum, we can use again this star. That means many. And it's also equivalent to the idea of a person may not work or may have worked in his professional life for between 0 and many companies. Or here we have also an example of a reflexive relationship. A person is linked with children if they have, if this person has sons or daughters, and one person is linked to a maximum of two parents, minimum and maximum of two parents. Okay, so with these numbers, we provide additional semantics in our class diagram, okay, to understand how the relationships will take place in real-time execution of this software. Okay, we can go a step further, and sometimes we want to combine the meaning that this is not only an association, but that there is an aggregation relationship. I mean, a company aggregates several departments. Or when we go to the library to borrow a book, we can establish, we can instantiate a loan object that consists or aggregates one, two, or three books. And this is linked also to the login of the library user. Okay, and we can go a step further in addition. Okay, here I am using the diamond symbol, and this diamond is blank, is white. Okay, I can go a step further and I can represent in my class diagram that this is not only an aggregation, but also a composition. This means that, for example, in this case, a car consists of an engine and a car consists of a body, okay, the structure of this car. And we consider when we use this diamond in black that the engine and the body cannot exist without being linked with this car. Okay, this is just an additional meaning that we want to represent in our class diagram. Okay. Okay. What can we do to translate these concepts into Python code? Okay. In principle, all the relationships that we usually define in analysis and design are, in many cases, binary relationships between two objects. And usually what we do is that association, compositions, and aggregations are translated into instance attributes. When the multiplicity of an object in one of the roles of the association is 1, we can just use an instance attribute. When we have a multiplicity that is different or bigger than 1, then usually what we do is to use a linear data structure. We need to use a list or a set or a supplementary structure where we can introduce several objects of the same type. Okay, here for example, we have a small class diagram where we have described that an industrial robot consists of a body and an arm. Okay. If we go to the code, we can see that we have defined the class industrial robot, and inside the init constructor, we have defined the attributes body and arm. Okay, so this is the translation to this relationship, this black diamond with the lines connected to body and arm. Very easy. We can provide an operation here that is called rotate body left. Okay, so we are going to move the body of the robot to the left. So usually when we have such an operation here in industrial robot, we will need to invoke to a related operation in the body. So here you can see that the implementation of this operation is that we invoke the body of the robot and we invoke the method rotate left. Okay, here we have also a small definition of the body. In this case, let's say that we have a composition and the navigation is usually only from the industrial robot to the body. So here you can see that in the constructor of the body, we haven't created an instance attribute to move to the robot. Okay, and here you can see that in the class diagram, we have used an arrow. This means that the navigation is only from the robot to the body. Okay, so this is just a way of defining structural relationships. And here we can see how we can translate that to the implementation. Okay, I hope that is clear. Okay. And okay, here I'm going to show an additional example that maybe is also interesting. For example, here, I don't know if you play cards, but I have an example of an aggregation. Okay, so we can have a deck of cards, and this aggregates objects of type playing card. And in the class playing card, we have an attribute that is the rank and the suite. Okay. If our objective is to define this data model, we are more focused on the data structure. In Python, there is something very interesting that is called data classes. So we can import these packets in Python, and we can add a special tag to annotate that this class is a data class. Okay. This also facilitates a bit the implementation and the code, because now is more intuitive, it's more natural the way we define the relationships or the attributes that we have inside this data class. For example, in the case of playing card, okay, in the class diagram, we can see that we have two attributes. When we have a class that is a data class, directly in the body of the class, we can define rank and we can define suite. Okay? We don't need to define the attributes inside the init attribute, the init method as before. Okay? And in the case of deck, we can see that the attribute in this case is the aggregation of the playing cards. So we can define as attribute cards. And the type of this attribute is a list of playing cards. We are using this data structure that we can import from the typing package in Python. Okay? And we can see a small example about how this works. Okay, so we can define a playing card, Queen of Hearts, and we can use also a default constructor, playing card, and we can pass the values for the attributes in the same order that they were defined. We can pass a value for the rank and a value for the suite. Okay, so this is the Queen of Hearts. And this is the Ace of Spades. So we pass A for the rank, we pass spades for the suite. And we can define a deck of cards. Okay, so here we have a default constructor attribute. So this expects a value for all the attributes that we have defined. In this case, the attribute is a list. So we have passed here an expression of a list. We construct directly a list with two cards, Queen of Hearts and Ace of Spades. Okay? We can define a third playing card, King of Diamonds, and we can use a method that we have defined inside the deck data class. A data class can also have methods, no problem for that. Okay, so here, for example, we have defined a method called addCard to add additional cards. In the implementation, we move to the list and we append a new value to this list, right? I think that, okay, here we can see also that there is a direct string representation for all the data classes. So if we use deck and we try to see the value that this displays, is going to display a string representation saying that we have an object of type deck, and in the attribute cards we have a list, and we can display the contents of the elements in this list. Okay. Okay, I'm going to tell also an additional, describe briefly an additional concept, and this is the possibility of making profit of polymorphism. I mentioned in the introduction that it's the property by which it's possible to send the same message to objects that belong to different classes. Okay, so we can see the usability of this. Okay, so for example, we have defined here an inheritance hierarchy for geometric figures. We have a shape, we have a circle, we have a square. Circle and square are subclasses of shape. In the shape class, we have defined two methods, get area and get perimeter. There is an additional detail in this example of code, I wanted to show you also how we can define that a class is abstract. What does it mean that a class is abstract? This means that there are no direct instantiations of this class. I mean, for us, when we are designing this software, we consider that shape is an abstract concept. It's so abstract that we consider that there are no real objects that belong directly to this class. This is just an abstraction because we have found that circles, squares, rectangles have some common properties. Okay, so you can see in the example that we have used, we have imported the class ABC and also the possibility of annotating something as abstract method. The class shape inherits from ABC, and this means that this is an abstract class. We cannot create direct instances of the class shape. And we can also define the method getArea, but it's impossible to obtain a value for the area if we don't know if this is a circle or if this is a square or if this is a rectangle. So we have annotated this method as an abstract method. This means that this must be redefined in the subclasses. For example, on the right, we have the definition of circle. Circle inherits from shape class. And we have defined the getArea method. This is a circle, and we know that the area is computed as the product of the value of P and the radius and the second power, okay, or the square value of the radius. Okay, so in the case of circle, we know how to compute the area, but only if we have a direct instance of circle. Okay, and you can see that in the shape class, we have defined this special method that returns a string representation of shapes. Okay, and we have implemented this as a string that obtains the value of getArea, right? Okay, let's say that getArea is a polymorphic method in the sense that we can have, for example, an object that is instantiated as circle, and we can invoke to the function print. This will try to return the string representation. There is no string representation directly. There is no method. There is no special method underscore underscore str underscore underscore in circle. So we will invoke the method in the parent class. Okay. And the method in the parent class, it's something that has been defined without knowing exactly which getArea method is going to be invoked. Okay, so just directly on real time, we link to the object and the method that is appropriate. Okay, so this is the potential of polymorphism. We can define methods in terms of something that is not really defined at the moment of writing this method. Okay. And last, I'm going to be fast. Okay, I just mentioned that in object orientation, I told you that modularity is really important. Every object is directly a small module, but in UML and also in Python, we have possibilities to define not just classes, which it's a small module, but we can define also groups of classes. In UML, we can represent this as packages, which are represented as folders. For example, here we have a package called raw materials and human resources. let's imagine that this is the software for a company selling products or manufacturing products. And if we go into the detail of human resources, we have classes like department or employee. Okay. So what can we do for modularity in Python? Okay. A module is a script file in a Python file, a file that use as extension py. A package is usually a folder where we have related modules, related scripts. And in Python, it's also possible to define a library, which is a collection of related packages and modules. Okay, but this is something that was introduced in the session that you had yesterday, and probably in other sessions they will provide more details. Okay, so now I'm sorry because I took a lot of time presenting these slides, but it's time that you try to exercise with some of the small examples that I propose you. Okay, so I will stop presenting this, and I don't know if you have prepared your Visual Studio environments or you are using Colab, but you can try to see how to develop some of these small exercises. Okay, so I don't know, maybe I can give you 10 minutes or less than that. 5 minutes for exercise 1, 5 minutes for exercise 2, exercise 3, and exercise 4. And I try to present the solution. Okay, this is something that is hidden, but I will provide access to that. Okay, later. Okay, so I mean, the idea is to go here and try to have a look at the first exercise. I'll give you some time. So here it explains. Okay, so maybe you can try to make something here, but later when you have time, you can try to do it yourself. But the first exercise, for example, is to define a time class where you can represent a specific time of the day with hour, minutes, seconds, and format. First, I present the UML class diagram, but you can forget, you can skip this diagram because below it explains you how to face step by step everything in this class, how to build the constructor, how to build the attributes in this constructor. Okay, so I give you sometimes, okay, just 5 minutes for example, and I come back with the solution. Okay. Okay. I don't know if you have time to start with the coding, but here you can see a small example. Okay, well, you can see more or less the solution. So the idea of this first exercise was just to define a very simple class where we can define, we can represent a time of the day, and we have defined 4 attributes at the end of the exercise. An attribute for the hour, for the minutes, for the seconds, and the format. Okay, and we have also provided special attributes to return the representation of the time, either using a universal format with the hours between 0 and 23, and a standard format that use the EM PM notation for the morning or the afternoon, and anti-meridian, post-meridian. Okay, so you can see that the attributes are defined inside the init method. You can see that these methods to universal format string and to standard format string are also instance methods, more or less very similar to the examples that we saw for the docs. We have also defined this special method to return a string representation. And here the implementation is that if the format that has been selected when defining the object is universal, we invoke to the method to universal format string. Otherwise, we return that just a standard format string. And here you can see some examples of use. Okay, we can define a variable time with one value. We try to print, we invoke directly the special string method. We can create distinct variables, and here we just have a small loop to ask the user through the keyboard, through the standard input, okay, some values for the time, and then we print that in the output screen. Okay, so I can try, this script is time.py. I can run that directly from my Visual Studio. I am in the loop. So if I put values for the hour, the minutes, and the seconds, and if I say that the format is universal or standard, that is more complicated, well, something that is different from universal, then it will return 11:23:23 p.m. Okay, if I want to continue, I type Y. If not, I finish. Okay, so you can, the second exercise is to define uh, a class called fraction. I don't know if you have time, but maybe it's better that I go directly. So you have in the solution folder in Moodle, you have three files. One is called fraction1, second is fraction2, the second script is fraction2, the third one is fraction3. So in fraction1 is just the first part of the exercise where I just need to define a fraction class for representing fractions, obviously, with numerator and denominator. Here, what I am trying is that you can see the utility of using this convention of the underscore for defining attributes. So instead of using directly num or then for the attributes, the point is that now we are using this convention with underscore num, underscore then. Okay, this is not something very restricted, but at least it means that when someone is using this code, they can understand that they shouldn't use direct access to the attributes. They cannot follow this recommendation, but at least we denote that with the underscore. We have also incorporated a method for the string representation, and we have incorporated a method to have the fractions in reduced form. I mean, we divide numerator and denominator by the greatest common divisor. Okay, so the example is really simple. Okay, so you can see that here we get the greatest common divisor. It's a recursive function following the Euclid's algorithm that you know very well. And here we also assign the sign only to the numerator. Okay, and we use this special operator to have the division between integers, because if we just use one backslash, then we obtain a flat value. Okay, so that's all. And here we have also a small main program that we can run, and we can see that this works. Okay, we have created this fraction, 8 for the numerator minus 12 for the denominator, and we can see that once that we instance this and we try to print f1, we can see that we have reduced the fraction and that we have the sign in the numerator. Okay. Next step. In fraction 2, we have in the exercise you can see that step by step we are aware that the greatest common divisor method doesn't depend on specific objects of the fraction class. So let's say that we can transform this method into a static method that doesn't depend on specific instances of the class fraction. Okay, so here we have just transformed the greatest common divisor into a static method. We use this tag, static method. And the difference with respect to fraction 1 is that before it was an instance method. So it had as first parameter self. Now it's just an static method. Okay, and this is a good way of programming when we identify that we don't need to incorporate the self argument because it's not an instance method. Okay, we define that as an static method. Okay, so this is the main difference, okay, in this second version of the script. What else? I have added here some typical operations between fractions, some static methods that receive two fractions as input parameters and we return a new fraction. Okay, this is not required in the exercise, but you can have also that in the solution, okay, in case you want to have a look. For fraction 3, the main difference now is that, okay, let's say that we want to protect better the access to the attributes. Okay, so instead of using this underscore convention, we can define that the attributes are now really num and then, but we are going to define special methods for updating the value of the attributes and returning the value of the attributes. Okay, in the exercise, in the statement of the exercise is well explained that usually when we have private attributes, we try to provide getter and setter methods. Getter methods to return the value, setter methods to update the value. Okay, but here what is recommended in Python is that we annotate that a method, the method that returns the value is annotated with the tag property. And the method that is used for updating the value is annotated with arroba, I don't remember now how to call that in English, num.setter, okay? So we can control the access to the attributes. It's not that when people use the notation .num or for returning the value or for accessing the value, for updating, okay, they are not directly using the attribute. They are invoking these two methods, one for returning the value, another for updating the value. And in the method that we have implemented for updating the value, we can also add additional code to control the values that we receive. Okay. In principle, Python is not a strong typist language. So you can see that we can instantiate a class with everything, even with incorrect values, and we are not going to take an error until the moment of the execution of this code. Okay. But here, we can control a little bit. For example, we can control if the value that we receive is an instance of an integer. And if it's not an instance of an integer, we can raise an error, a value error here. Okay. And in the case of accessing the value for reading the value, okay, you can see that only in this method is the place where we are defining the attribute. The first time that we use underscore num. In the init constructor, when we type self.num equals none, in reality, what we are doing is to invoke the method that we have annotated here as setter. Okay, we are sending the num value that we have received as input parameter to be stored in the internal attribute that is called underscore num. Okay. So, and you can see, you can run again the main method, the main program, and you will see that this works. Okay. I don't know if you have any questions for this.
Well, I have a question for the first exercise of time. Why, when you run it, the first thing that appears is like an example. I didn't really. Is that like important for the code, or like if you run it, it says 12:30 a.m. 1:30 p.m. Like if you just click run on the code, sometime like that. Yes.
Mhm.
Why did you add that? Just as an example, or
This is just an example, yes, and
okay, okay,
and this is a comment to display what you should see on the screen.
okay, yes, okay, okay. Because I see that now you can type some different numbers and it works. So it's just an
Yeah,
example.
this is just a main program to make you familiar with the code and just to play,
Okay, okay. Thank you.
in case if it is helpful for you. Okay. There is an additional, okay, there is an additional example where I also propose you to complete the shape class that I presented in the slides to define the square subclass. Okay, such, and with this exercise, the objective was that okay, you can define a subclass. You see that we redefine the method getArea that now has a different implementation with respect to circle. In this case, the area is computed as the square power of the side of the square. And you can see that in the main program, we are defining a list of shapes, and in every iteration of this loop, we are going to execute to have 10 iterations. In every iteration, we create randomly an integer value using this function from the np.random package. And if the integer that we generate is odd or even, we decide to create a circle or a square. Okay. So I mean, if the rest of the division is 0, we create a circle. If the rest of the division by 2 is 1, we create a square. Okay. And here we invoke the print method. The print method um, is a method that I have defined in shape class, and it iterates across a list of shapes. For every shape, we invoke the print function. The print function of an object of a class derived from shape is going to use this special str method. And you can see that we are invoking the correct get area method in every case. Okay, so if you run that, you can see that it's generated 10 objects with random values and random areas, and that's all. Okay. And the final example, I'm sorry because I don't have more time for that, but maybe later you can work on your own. You will see that there is another statement for the definition of polynomial expressions of any power. So I mean, this is like an aggregation of terms in different powers, and every term has a power and a coefficient. And I have defined the term and the polynomial as data classes to demonstrate the last concept in the slides. Okay, so a term has two attributes, power and coefficient, and we have methods to evaluate a term for a specific value x. And in the case of polynomial expressions, we have lists of terms. Okay, and I have incorporated some methods also in the statement of this exercise. It asks to define these specific methods step by step, but I don't have time. So you can have a look, and this is an example of data classes and how we can define aggregations. Okay. Okay, so that's all from my part. I hope that you have enjoyed. I know that it's a lot of material in very short time. I will put in the chat my email address in case that you have any question related to these exercises. So I will be happy to reply. Okay. So thank you all for your attention, and that's all from my part.